Good morning. So I have one announcement before I introduce the speakers. So the second talk is going to start at 11:45. That means 15 minutes before the usual time. And in the afternoon, the first talk is going to be at 2 p.m., not 2:30. So now it's my pleasure to introduce Wieslawa Niziol from Sorbonne University and CNRS, and she will speak about geometric Poincare duality for p-adic Pro-Étale Cohomology of Stein spaces.
A few words about the basic properties of Stein spaces as we go on. And for the moment, you can think about the Drinfeld upper half plane or open disk, for example, and fixed dimension D. And then in some topological universe, so topological category for us is going to be derived category of solid QP modules. And in that category, we have a duality morphism, quasi-isomorphism between Pro-Étale cohomology of X, C, so geometric QP, and all of this has topology now, and this is quasi-isomorphic to R home in a category which we call category of topological vector spaces of Pro-Étale cohomology with compact support now, XC QP, the twist D, and shift to D. So the numerology here is the one you are familiar with from Étale cohomology, for example. You have the right twists. And I have to explain what these objects are actually. So maybe left-hand side doesn't need so much explanation, but the right-hand side does. Okay, so let me explain these objects. Okay, so what is TVS? So this stands for topological vector spaces. So capital V, capital S, capital T, right? So many of you are probably familiar with these objects. So VS are defined as, for our purposes anyway, as V shifts of QP underline modules on perf C, where for me, perf is going to be the category of always affinoid perfectoid spaces. Okay, so what changes for us to have this TVS? So we consider now shifts not with values in QP underline modules, but shifts with values in condensed QP modules. And sometimes I will use VS box when the values are in QP solid modules. Okay, so basically we consider shifts on affinoid perfectoid algebras, but we put for V topology, but we put horizontally topology on them. Okay, so on every set you have, on every open set you have a topology. Okay, so this is one thing I wanted to say. Second one, so we needed to figure out what do we take for Pro-Étale compactly supported cohomology. So in the end, and I will skip later this subscripts Pro-Étale compactly supported cohomology, the one we wanted to consider, in the end, turned out to be the same as Étale cohomology with compact support defined by Huber. So Huber, in a short paper, he defined So in his book, he defines cohomologies with torsion coefficients for p-adic spaces, but he has a short paper when he considers ZL or ZP and QP coefficients and étale cohomologies. And the one with ZL coefficients or QL coefficients behaves in the right way, but with QP coefficients, what he defines is actually pro-étale cohomology. It's not the right étale cohomology with compact support, I mean. But here we are in a Stein case. So this definition, so for this definition, X can be anything, any resolvable rigid space. But if X is Stein, then we can go back to classical definitions which were used of compactly supported cohomology, which were used by van der Poot and many people after to study the RAM cohomology with compact support of Stein spaces. So we just copy these definitions, and they are the following. So, and these are the same. These give you isomorphic theories. So we define pro-étale cohomology with compact support as mapping fiber of pro-étale cohomology of X and the pro-étale cohomology of the boundary of X. And this is just a notational thing, this boundary here. So what do we mean by this? The cohomology of the boundary of X. I should put C everywhere, sorry. Boundary of XC is defined as the colimit over quasi-compact open subsets of X, for that matter, or XC, of pro-étale cohomology of X. So let me write this U, maybe I prefer U. XC minus UNC QP coefficients. So many variants of this definition are possible, as you can imagine, but this one is a short one. And one thing to keep in mind that actually this cohomology of the boundary is an interesting object by itself. So if we look at the coverings of the Drinfeld space, maybe not so much pro-étale, but its étale version seems to be related to constructions of this type, which appear in p-adic local Langlands as defined here by Colmez. So these are interesting objects to study. Okay. So I defined it's just a notation. It's a square bracket. It's something that Colmez defined in his constructions in his work on p-adic Langlands. Okay, sorry. Okay. So one thing I still did not explain is that I am taking R home on the right-hand side there in this category TVS, but these objects a priori on the inside still don't have a TVS structure. So you have to put TVS structure on everything. So TVS structures. So we like to call it geometrization. That is, instead of C, you want to vary C in families. So C has to be replaced by S inside the perfectoid spaces. Okay, so how do we do it for the pro-étale cohomology with or without compact support? So we replace this object, which a priori is, no, wait. So we replace this with an object which I will denote in this block R, QP, such that S is mapped to the corresponding cohomology of X base changed to S, QP. So that's the most naive VS structure on Pro-Étale cohomology, and this is the one we take. So
everything condensed, so that you also parameter which is the condensed, and so you base change the excess cost that for finite set the cohomology of this. So it's kind of doubling the exchange.
Yeah, you have to do that, yes. But let's stay with this. This is simplest. So this is a sheaf now for the V topology, V topology, and this is our geometrization here. So in that statement above, I actually should replace R gamma with this block R. Okay, so having this, let me give you a motivating example. So this is example which we like to give. And many of you probably saw it, but let me do it again. So D over C is an open unit disk. So already in this example, you see not only the shape of the duality that we should have, which was not a trivial guess, and then you also see all the topological properties that you need to have to actually pull off this duality topologically. So non-zero groups here. We have the following. So we have H0. So the twists here are Tate twists. I keep track of them because sometimes we want to descend to the arithmetic setup. And then the Galois action is important. So H1, so these kind of things you can compute, for example, using some basic comparison theorems. We have functions on D modulo constants. And then we have one more group, which is H2 with compact support. And then you get some constants, QP constants. And then you get functions on the boundary, modulo the functions on the total space, and some twists. Okay, so what kind of pairing you can see here? And you are going to see, so you can disregard the QP spaces. There is some kind of trivial QP pairing here, but here you are going to see Serre duality. So let me write this. You see Serre duality. So we are in dimension 1. So we have isomorphism of O mod of OD mod C with the differentials. And then we have O of the boundary, just by the definition, which is similar to that definition of compactly supported de Rham cohomology. This is going to be H1 with compact support of O. Okay, and then we have Serre duality, which tells us that the dual of one is the other. Sorry, this is not X. Okay, so these terms are in Serre duality. So the degrees don't agree. If you try to build a naive Poincaré duality, you will get mixed degrees. So you would have to aim for Verdier duality. So that means that we cannot just naively pair these things. But if you work in TVS, there are some non-trivial X groups which appear. So let me put the table here. We have, so everything is in TVS. QP and QP is just QP. And X1 QP is 0. So this is, you would expect. Then hom from GA to QP, that's 0. So this comes as a surprise maybe. So what is GA? GA is just S going to OS. And it's the VS structure that forces this absence of any maps here. And now if you look at X1 of GA by GA, no, sorry, GA by QP1, then you get C. So these are not relative groups, these are the absolute groups. So you just get C. If you take this into relative, change this into a relative shift, you are going to get GA here. So what is the generator here? It's something coming from the fundamental exact sequence, familiar object. You have a period ring as a crystalline as a VS, as a sheaf. And then we have C. And here we have QP1. So a familiar object. And in fact, there is no higher X in this set. So if you put these two things together, then you can, at least heuristically, you can write that H1 D QPJ should be X VS or TVS of H2C D QP 2 minus J QP. So you get a reasonable formula. So this was kind of the starting point of this whole story, really. But you see several issues here either way. So I told you what are the X groups of GA by QP, or I missed one there, no? Oh, no, it's okay. But in fact, when you look up there, the spaces O boundary D or OD, they are infinite dimensional, right? So you have to, so you don't have, so one remark, that we don't have objects like X, GA, QP in TVS. And these are what we call Banach-Colmez spaces. So these are VSs with some finiteness conditions. We don't have this finiteness condition. This object is actually some kind of V. Well, it's more like V tensor GA. And in our case here, for compactly supported, this is a space of compact type. Compact type in the traditional terminology, not in the Clausen-Scholze terminology. So these are colimits of Banach spaces with compact transition maps. So they have very strong duality properties. So this actually gets out, and we have a dual here. And so that's the way we reduce these computations for these large spaces to a dual of something which is really constant. So here, all of these things can be geometrized and can be made into V sheaves. But this one is kind of comes from the outside of the story. It's constant. But you basically, all the difficulty here now appears in this, which is, again, just extension of Banach-Colmez spaces, which we can deal with. So you see all these difficulties already in this example here. Okay. I will have to raise this. So I just want to state a quick corollary, because as I mentioned, all the higher X groups vanish. So actually this Verdier duality, which I wrote at the beginning, which in principle involves all the X groups, is actually involving just Hom and X1. So let me write this as a corollary. So a duality exact sequence. So there exists a short exact sequence. And again, it's in the solid universe. And it looks like that. We have Hi Pro-Étale. Then we have Hom functor, Hom part in TVS between H2D minus I compact support twisted by D and QP. And here you have an X group. So X1 with QP. And what is this object here? It's H2D minus I plus 1 of XC QPD. So the duality has a simple form. So what is the proof of that? Well, if you use the R-Hom spectral sequence, so R-Hom spectral sequence, then it suffices applied to that theorem 1, then it suffices to show that all the relevant Xi's involving these compactly supported cohomologies, that those are 0 for I at least 2. Okay, so what's the idea here? So this reduces to the following proposition, that if you have two Banach-Colmez spaces, so to recall, maybe to fix some definition here, so these are V sheaves generated by QP and GA and closed under extensions. Then I in this TVS between these two are 0. And in fact, what we claim is maybe this follows from, so let's write it this way, that this will follow from a claim that X in these topological vector spaces are the same as X groups when you forget topology and you just do vector spaces. And the fact that these groups vanish in degrees higher than 2, is a result of Anschutz-Lebrun. And this is proved by a reduction to a mod P result of Brin. Okay. So why would you believe this kind of result, that this, whether you put topology or not put topology on these things for these finite type kind of objects, it seems not to matter. So in some earlier work with Pierre, we actually computed. So we were always working in these topological vector spaces in our geometrization of comparison theorems and stuff like that. And there we computed X1s between GA and GA, GA, QP, etc. And the results were exactly the same as you would expect in the case when you forget topology. But this kind of techniques, very explicit techniques, will not give us this part here. So for this part, we have to use McLean resolutions in these TVSs. And there you look at the terms of the McLean resolutions and what you get. So you have to put a topology on the mapping space of between two affinoids, for example, and to get some kind of Yoneda lemma in that setup. And there what you get from these McLean resolutions is cohomology of the affine spaces with values in the sheaf O or QP. Now, you know that all of those are represented by complexes of Fresher spaces. A complex of Fresher spaces is topologically exact, so strictly exact, even only it's algebraically exact. And you know it's algebraically exact because it just represents usual cohomology. So that's the way the argument goes here. So we try to prove it by some kind of manipulation with sites. I mean, we try to find simpler arguments for this, and this so far didn't work. I'm not sure we can get away without these topological Yoneda lemmas. Okay, so this is the corollary I wanted to mention. So before sketching the proof, I want to make few remarks still here. So let me just make few remarks. So the first is a question. Can we flip the usual and the compactly supported data in that theorem, in the first theorem? That is, can we claim that we can recover compactly supported cohomology as R home from the usual cohomology? So I don't know. And so what is the issue? So we use the fact that these cohomologies with compact support are of compact type. So compact type, then we pass from compact type to Smith spaces. Smith spaces are projective objects for this topological situation. And we essentially use that. On the other hand, if you work with this and you take R homes from this, these are nuclear Fresher. So again, the nuclear here is in the terminology, classical terminology. So nuclear Banach are finite rank necessarily. So these are nuclear Fresher, and you are asking whether, I mean, you have to work with objects like that from nuclear Fresher. And here we bump into questions of extensions of Banach spaces or extensions of Fresher spaces. And it's possible that if we extend our set theoretical universe, these things are actually zero the way we want them in higher dimension. I mean, for higher X. And then we have the right duality. Maybe we can get it without that, I don't know. But at the moment, we don't know whether this is true. So there is essential difference between compact support for these applications and nuclear Fresher. Okay, but let's assume that we have it. So assume we can. If we can do that, then
this is literally a question that's independent of ZFC. So I think this is definitely false in some models, but definitely true in others.
But I thought in that universe in which they were proving there is no extensions was consistent with our universe, no?
Yeah, let's say. In some models of set theory it's wrong, in some models it's true.
But if in the one we like?
I don't know which one you like. When we wait.
Probably the same.
The question is definitely independent.
Okay.
You might as well decide to work on one stream.
Is it related to the usual thing, large cardinals, or is it different kind?
No, it is independent of large cardinals. You just need to make the continuum large enough. If you just add 2 to the aleph omega many cone reals, then it's fine.
Well, one thing we thought could have saved us was that, you know, we don't have general R-homes, but R-homes in the field, right, QP. So for X1 of...
yeah, I'm pretty sure that just for these kind of, like just infinite product of QPs or similar things, you already get higher X.
Higher X, okay.
Also set theory, but.
Okay. So there's no X1. You can see that there's no X1, but the higher X, okay. Yeah. But let's pretend that maybe this is true and see what happens. So if this is true, then you can, you know, you have both dualities, and then you are going to get a duality for the boundary. For the boundary of X, see? So how does it look like? You have R, so I'm going to write it in the relative, I mean, as V shifts now of the boundary with QP coefficients. Is the relative interior home of cohomology. Now, no compact support of the boundary, QP. And then the sheaf is 2D minus 1 with QP. Okay, and so slogan could be here that the boundary is real manifold or real space proper of dimension 2D minus 1. So that's the duality for the boundary. So the boundary is self-dual. And in the case, or in the arithmetic case, we were able to prove this kind of results for the boundary of the disk by hand. But here, I don't know whether we can actually pull it off without these issues with logic. Okay, another result, another corollary I want to mention of the. Well, I don't know, because we wrote everything starting from DVR at the moment, because we just wanted to make sure everything is correct before we do things over C. It's simpler over DVR because we can detach, as I will write in a moment. Biederam plus has a K structure, but not C structure. Okay, so we don't have to worry about, we just can tensor instead of doing some extensions. Okay. But possibly, yes. Okay, so second is arithmetic duality. So this is a theorem of a student of mine from Paris, Jussieu. And so he proves arithmetic duality, but I will mention it later that the proof of the geometric duality has two paths. We prove duality on the curve, and then we descend to TVSs. So he actually does not descend to TVSs. He just takes the duality on the curve, and then he uses, use duality on the curve, on the Falk-Fontaine curve, and then descend to the Galois setup. So descend by Fontaine's theory of almost CP representations. Almost CP representation. Okay, so let me just mention the statement, which is the one you might expect maybe from some previous works. So cohomology groups actually. Now arithmetic means that this is just X, not X sub C. Now the twists are actually important here. Compactly supported. So these are nuclear fresh air and compact type as before. But here you have to work a bit to actually prove it. And second, that if we work in the, yeah, okay. So everything is topological again. We have that you have the arithmetic duality, which looks in this way. So the numerology is arithmetic. So you add the indices coming from Galois duality. So 1 for a twist and 2 for a shift. And in this way. But one thing what happens here, which is different from this situation, that you actually get really Poincaré duality. So you write it that way, but actually what you get specifically is a duality between HI, when you pass to cohomology and because of topological properties, and H2D plus 2 minus I. And you can now write C and nothing and C. So the duality works both ways here. So the arithmetic duality simplifies considerably. Okay, so that's all the remarks I wanted to make. Now I have to erase some boards. Maybe I still have one here, no? So I wanted to sketch the proof a bit. So the proof has two parts. One is we prove duality on the curve. And it's on the curve that you see some magic happening. Okay, so let me pass to the curve here now. Okay, so let me restate. So proof of this first theorem. So I want to restate in TVS, so relative version. So I have the sheaf representing Pro-Étale cohomology and interior home. Okay, so that's our statement. So in the first step of the proof, we have, well, first step, let's pass to symptomic cohomology. So before I get on the curve, symptomic cohomology. Okay, so let me just mention that by the work of many people, I will mention some names in a moment. Compactly and non-compactly supported Pro-Étale cohomology can be computed by symptomic cohomology, compact support or not. Now I have to assume that R is large to get that. R larger than D, maybe it's enough, maybe D plus 1. Where D is the dimension, so D is the dimension of X. So this is comparison, so this is what is called comparison of basic comparison theorems. Now, before I mention maybe names, I should explain what is this symptomic cohomology that we use. So this is the crystalline symptomic cohomology here. So it's a classical object by now, introduced first by Fontaine-Messing. But we want to write it in a way which I trace back to the paper of Bloch, Kato, and Tamagawa numbers. This is the shape of symptomic cohomology that is used by number theorists to study regulators, Euler systems, etc. Is because you can actually compute with it. So I'm going to write it that way. So symptomic cohomology is going to be defined as the mapping fiber of Kyoto-Kato cohomology geometric one. So the geometric one lives over C breve, which is the fraction field of the Witt vectors of the algebraic closure of the residue field. And the tensors here are with VST plus of Fontaine. And then we take derived invariance for Frobenius and monodromy. And then we take Kyoto-Kato map into the RAM cohomology with compact support. But we take the infinitesimal one over B the RAM plus, and then mod out filtration R. Okay, so let me give names to these things before I. So what we are going to have is a triangle, distinguished triangle, with this object here, which I will call X, HK for Kyoto-Kato, XCR, and this object here, which I will call DR, XCR. Okay, so a few remarks. Well, one remark. Let's make one remark. Yes, that the brackets I put here means derived. Yes. Yes, everything is derived. Yes. And so one remark I want to make for the future, I am always going to be work with C here, but so there exists a version in families where C gets replaced by any perfectoid, affinoid perfectoid over C. So C gets put here, and then C doesn't get put here, but C gets put here. So all the period rings are which are period rings attached to C. There should be tildes here to be precise, but never mind. Are actually now attached to S. So you see what happens when you do this in families, geometrize. So in the usual comparison theorems, you think that you take the Galois action here on the coefficients, so the Galois action on étale cohomology, Pro-Étale cohomology, and via comparison theorem it gets trivialized in the sense that it's all hidden in the period rings, right? So if you do it with S in this VS universe, a similar thing happens. That is, this structure of S, which is here in the coefficients, gets completely trivialized and becomes all hidden in the period rings. So the slogan here we like is that all VS structure, so all VS shifts, so to speak, are attached to period rings. To period rings, I guess we write them in this way, to period rings. And the rest of the story, so like this object, it comes kind of from outside, so it's, so to speak, constant. So this is constant. So we trivialize the VS structure. So we use it in the computations all the time. Yes, thanks. I was just going to explain these things. One thing I want to mention is that So this is due to a number of people. So let me mention our work with the Spinescu. And then our work with Pierre. And then the compact version is an ongoing work with Ahinger. Okay, so we are in Stein spaces. So these objects actually, especially this one, are very simple. So I want to explain what they are, because again, we use the fact that they're very simple. So what are these objects? So let's look at the Theorems part first. So we are on Stein spaces. So Stein spaces have trivial, coherent shifts are acyclic on Stein spaces. So the Theorem cohomology can be computed by the complex of global sections of the Theorem complex. And there is third duality, and the only compactly supported cohomology that survives is the one in degree D. So if you look at the Theorem cohomology with compact support, which is computed by this formula, as I stated at the very beginning, you get a complex HD of O, HD of omega 1, and HD of omega D. And this is all starting in degree D, so it's shifted by minus D. So it's very simple, right? Very simple complex. Okay, so now what happens if I look at this B-Theorem plus cohomologies, which is essential for us? So because we are over DVR, then this cohomology is again very simple to write. So I just write the usual one, the compact support you can imagine. Now over C, B-Theorem plus. So now this is complex, just the original complex twisted by B-Theorem plus. And in fact, so this is over K. B-Theorem plus, etc. And now this can be filtered. So what is the filtration R of this? So you have OX tensor T R B-Theorem plus, and then omega 1 tensor T R minus 1 B-Theorem plus. So if you mod out these two, and you look at this object, which I called XC, XCR, which is the quotient of these two, what you get is OX tensor B-Theorem plus mod TR omega 1 X tensor B-Theorem plus mod TR minus 1, etc. So this is something you really can put your hands on. It's very simple. Okay. On the other hand, the disadvantage here is that you have huge spaces, right? So again, these are nuclear fascia. And these guys are compact type. So now what about the second factor? So second factor involves something called Hiodo-Kato cohomology. There. So let me just mention this. So Hiodo-Kato. Okay, so Hiodo-Kato cohomology. So that is some kind of incarnation, some extra structure on the Theorem cohomology. So for, okay, let me mention maybe this way. X, C. So we have Hiodo-Kato isomorphism. You can even write it with C here, between this and the Rive cohomology. And this is the main tool you use for studying properties of Hiodo-Kato cohomology. You reduce to the Rive. You know usually the Rive behaves very well. So you know Hiodo-Kato behaves very well. So Hiodo-Kato has extra structures, phi n and some residual Galois action, but it doesn't care about the filtration here. So that's important. And now, so whatever you know here, you transfer here. And one of the things is that if you can overconverge the Rive cohomology, so you can look locally on your space. And if you look locally on your space, then this in overconvergent setup, this becomes finite rank. So if cohomology, Hiodo-Kato cohomology groups are of finite rank, then what you get here is actually perfect complex. And this object H, K, X, C, R, this is actually Banach-Colmez space. Okay, so in our topological dealings, we have two kind of separate issues. Here we have some limits, but they're not that important. When we end up with BCs, which we know how to deal with, here we have some large spaces, but they have good duality, and they are also basically constant. They're constant on the VS, so they can get out. So that's the way to deal with this.
Something is bidimensional when we evaluate it without under which conditions something is bidimensional in a naive sense, and it is good.
No, it's finite dimensional C breve vector space. Finite dimensional C breve vector space.
When you evaluate that, that's the trivial condensed set.
Well, yes.
Everything is with condensed parameters.
Yeah, but
saying the finite dimension could mean as a condensed object or the naive object. That's the meaning as a condensed.
It's in a naive sense, it's finite dimensional, so it's finite dimensional as a condensed as well. It's a CV vector space simply. And this embeds into the condensed words as a CV vector space.
So in the classical functional analysis,
it's a good cohomology. It's really topologically CV vector space. It has right topology.
Like in classical functional analysis, of cohomology both with finite dimensions is separated.
It is separated. Mm-hmm. Yeah. So okay. Okay, so let's now pass to, so this was to explain maybe these definitions of symptomic cohomology. So now why would we, once we know this symptomic comparison, why would you now believe in existence of Poincare duality? Well, so Pro-Étale, we just wrote this. Data is equivalent to some data of Hiodo-Kato cohomology and the Rive cohomology. And this is encoded in the symptomic. This is equivalent to symptomic data. And now the Rive Poincare, there exists the Rive Poincare duality. And even filtered. And by Hiodo-Kato comparison, you can deduce that there exists actually Hiodo-Kato duality. So you think that you are done, right? But of course, we knew that for a long time that these things have dualities and so what? I mean, it wasn't clear that it says anything about the duality on Pro-Étale cohomology. So why not? It's because in the definition of symptomic cohomology, the data of Hiodo-Kato and the data, the RAM data are kind of intertwined, and you take actually Frobenius invariance in the Hiodo-Kato here, so that mixes up things. So the question was how you can separate Hiodo-Kato data and the RAM data and forget about the Frobenius. So how to separate Hiodo-Kato and the RAM data. And forget about the Frobenius. I don't specify in which sense. So the magic, so this happens on the curve. So we have step 2, we have duality on the curve. So by which I mean the Falk-Fontaine curve. So I only have like few minutes left. So let me just mention what happens here. So to this symptomic cohomology, you can associate quasi-coherent sheaves on the Falk-Fontaine curve. So these are quasi-coherent in the sense of solid quasi-coherent, in the sense of Andrejchev. And we do it in an elementary way, but construction we have is probably the same as the one done by Guido Bosco. And so instead of defining it, definition is very simple actually. We define it, maybe if I have some time. But what are the properties of these sheaves? So if you look at the fibers, here's a fiber on the X curve, so that's an X curve. If you look at infinity, and then at a different point here, so if you look at fibers of our, not stocks, but fibers of our complexes here, then at this point, what we get is Hiodo-Kato cohomology over C breve tensor with the residue field at X. What you get here at this point as a fiber is the filtration R of the RAM cohomology over B the RAM plus tensor over B the RAM plus with C at infinity. And now, if you believe that what I'm saying is correct for this, you see that these sheaves have Poincare duality, because here on these stocks, you will have Hiodo-Kato duality. And here at infinity, if you look what this object is actually, then it's going to be just direct sum. So you look at this expression, which one? Oh, this one here. You look at this one, and you tensor it with C. So what do you get? You get Hodge cohomology. There are some shifts and twists. You get Hodge cohomology plus some Tate twists. And you have the RAM duality here. So that's the way you have separated the two data, and these two dualities transfer to this duality, which gives you the duality on the curve, and then you have to apply descent data to descent to TVS. So let me just mention one thing here, because I wanted to mention it earlier. So I can descend from, so if I have quasi-coherent sheaves, like for example, these ones here, I can apply the push-forward functor to them, and we end up in TVSs. And this functor is going to preserve the proof, these R homes between these objects which appear over there. So this R home C of OSS, we call it. If you push it forward, you are going to get these guys inside. So you have to compute that, but it's correct. So R homes are preserved by this kind of push down functor, but not true for tensor products. For tensor product, this doesn't work. And why do I want to mention it? Because if you look at this picture here, these fibers, but you can make it formal, you see that we have a Kinet formula, for example, for these spaces. That is, we have a Hyodo-Kato Kinet formula because we have the RAM Kinet formula, and we have Hodge formula because we have Kinet formula for differentials. So you have a Kinet formula here on the level of the curve, but unlike the duality morphism, the Kinet formula does not descend naively, okay? And if we know that our cohomologies, these guys are actually going to be represented by perfect complexes. So if you descend, you have Banach-Colmez spaces, then we can modify this tensor product on the level of Vs to kind of make it Banach-Colmez tensor product, and then you get a Kinet formula. But in our case, we don't have BCs. We have some, what we call QBCs, so we don't know what to do. Not yet, anyway. Okay, thank you, everyone.
Just in the beginning, that's a space for Stein.
Yeah.
Statement should globalize, right?
Statement should what?
Statement should globalize to all like possible.
Well, right. So I think we know now the RAM duality for partially proper, right? For maybe it's stated in.
Main theorem was just for complexes, right? So there should be complexes should.
Yeah. So our feeling is that maybe, but because of these topological issues, we don't completely know. But it's true that everything is reduced to third duality or duality for the RAM cohomology. And all these comparison theorems and everything works for the partially proper setup. So that's not a problem.
So tau was the projection from FF.
Yeah, so I just took it as a notation. So you take your quasi-coherent sheaf, and then for every S, so R, so this one is defined by sending S, which is a perfectoid, to R gamma to the, so everything has to be done for the relative curves of these sheaves restricted to defined on these relative curves. So we don't do it for very general sheaves or anything like that. So for our sheaves, you can prove there is actually a descent here. So these are really V sheaves. So this is the functor.
So maybe just a stupid question. Do you have any picture of what would happen for Étale cohomology instead of Pro-Étale?
No, I mean, we really didn't think.
If there are no further questions, let me remind you that the next talk is at 11:45. And now let's finish.